Hello, everyone. Thanks for coming to my talk. I would also like to thank the organizing committee of Cosmology from Home for organizing this amazing event. So I will be talking about scalar tensor mixing from icosahedral inflation, which is a project that I did with my advisor and was published at the end of last year. So I will be introducing to solid inflation and icosahedral inflation, and then talk about how if we include non-minimal coupling in those cases, we can introduce anisotropies to power spectrum. And then I will talk about the main course, which is the mixed tensor scalar power spectrum and some observational implications, with some conclusion remarks at the end. So what is solid inflation? Solid inflation is a model that uses a triplet of scalar fields as the inflatons to drive the inflation. The triplet of the scalar field satisfies internal translational symmetry and rotational symmetry. These are both internal symmetries. And we can use such a triplet to build an effective field theory of a solid. And the building block to the lowest order takes this form to the lowest order in derivatives. And with this, we can write down the total action by coupling to gravity. And here you see the Einstein-Hilbert term and the solid action term. Such an action admits FRW solutions for the metric, which is also why we can use it to describe cosmology, or use it to describe early universe. So we want to give a VEV, a non-zero VEV to the scalar fields, which is equal to the space coordinates. And of course, this introduces a spontaneous symmetry breaking. But at the same time, if you think more carefully, the background values, the background metric, and the of the metric and the scalar fields are invariant under a combination of spatial translation and internal translation, as well as a spatial rotation and an internal rotation. You can think of it as we are using internal translations to cancel out the spatial translation and vice versa. Such a combination is called the Unbroken subgroup under spontaneous symmetry breaking vocabulary. And under this rotation, we can construct an action of the perturbations of the metric, denoted H, and the perturbations of the scalar field, denoted pi. And such an action is invariant under this unbroken subgroup. So at the end of the day, we can do the expansion up to 2 derivatives and second order imperturbations from our original action and obtain the action for the perturbations in the following form. Here we have the tensor mode, which comes from the perturbation of the metric. We have the transverse component of the perturbations of scalar fields, which gives rise to a vector mode, and the longitudinal component of the perturbation of the scalar mode of the scalar fields, which gives rise to a scalar mode. And from here, we can start our calculation of power spectrum and anything beyond. Now, for icosahedral inflation, we go one step further by specializing from a generic SO3 rotational group to a discrete subgroup. Basically, our triplet will be invariant under a discrete subgroup of SO3. The question we want to address here is, can we make the system intrinsically anisotropic while giving isotropic background and scalar spectrum for perturbations? And of course, the quick answer is yes, otherwise I won't be talking about it here. A more elaborated answer is that we can construct a 6-index tensor that is anisotropic and invariant under the icosahedral group. And the tensor can be given in this form. Here, gamma is the golden ratio, and the delta I plus 1. The I plus 1 is to be understood with a mode 3. And for example, here, this 6-index delta function is anisotropic. So at the same time, any other 2-index or 4-index tensors that are invariant under icosahedral group are necessarily isotropic. You can see the proof in the original paper of icosahedral inflation. And in there, you can also find the proof that the icosahedral group is the only group that satisfies all of these requirements. We can take a closer look at the tensor to further separate out the spin 6. The technical term is the spin 6 component of it, which is also traceless under contractions of any between any 2 indices. Now, why do we need non-minimal coupling? This is because that if we were to investigate only minimal coupling, even though we have this 6-index anisotropic tensor, it can only affect these 3-point functions, and all of the other power spectrum are still isotropic. However, if we allow for a non-minimal coupling, we can include an interaction term for the tensor modes that is a contraction between the 6-index tensor and a combination of tensor modes, tensor fluctuations. This term will give rise to a anisotropic part of the tensor fluctuations. Here, this delta c square and the z are constant at 0th order in slow row. This delta c square describes the size of the of this mixing term, and z can be set to 1. Such an interaction term can be constructed from a non-minimal coupling term that takes this following form. So we can now start our calculation of power spectrum by including this interaction term into the tensor mode fluctuation, the action for the tensor mode fluctuations. And we do this to the 0th order in slow row. And then with the usual polarization decomposition, we can arrive at the final result here. We see that there is a anisotropic component to the final tensor mode, whereas this delta c squared describes the size of the anisotropy, and all the anisotropy structure is encoded in this M matrix. So now that we can have a term that gives rise to anisotropy in terms of tensor mode, the same non-minimal coupling term that we saw before can also give rise to a mixed tensor scalar term, which takes the form here. And after some tedious algebra and separating the longitudinal and transverse component of the pi fluctuation, we arrive at the final result here for the tensor scalar mixing power spectrum. Now, it is interesting to compare this to the tensor mode. That is, the tensor scalar mixing can be compared to the tensor mode through this ratio here, which indicate that the tensor scalar amplitude can be larger than the tensor spectrum if the delta c squared that controls the size of the tensor scalar mixing is larger than the tensor to scalar ratio of solid inflation. We will be assuming that this is true in the following discussions. We can take a slightly further look into the anisotropy structures of this result. Here we plot the absolute value of this M structure, which captures the anisotropy of our model. And we can see that all of the spikes here are aligned with the edges of a icosahedron, which indicates that this structure is indeed invariant under icosahedral symmetry. It would also be very interesting to compare our model with another model called the anisotropic inflation. You can check out more details about it from in those papers that discuss that deals with endotropic inflation. Here, I just list out some interesting aspects. The first one, which is also the more fundamental one, is that in our model, the background metric is completely isotropic. There is no anisotropy in the background. And the source of anisotropy in our model comes from the fact that we can construct a tensor that is anisotropic under icosahedral inflation, and at the same time invariant under icosahedral inflation. Whereas in anisotropic inflation, the background metric is anisotropic intrinsically, anisotropic by construction. And there's no way, there's no other source of anisotropy. Everything comes from the anisotropy of the background metric. And by everything, I mean every anisotropies in this model. A rather simple difference is that in our field, in our model, we use a triplet of scalar fields, whereas in anisotropic inflation, they use only one scalar field. Another interesting difference is that in our model, the scalar power spectrum is kept to be isotropic. There's no contamination, if you wish, to the isotropy of the scalar power spectrum. Whereas in anisotropic inflation, there will be a small anisotropy included in the scalar power spectrum. Basically because you have an anisotropic background metric. And lastly, the most interesting difference in my view is that in our model, it is possible for the scalar tensor to tensor ratio to be larger than 1, depending on the size of the tensor scalar mixing and the size of the tensor scalar ratio. But this value is unrelated to how the scalar power spectrum behaves. On the contrary, in anisotropic inflation, this ratio has to be suppressed by a small anisotropy. What I mean here is that the scalar tensor mixing is allowed by introducing anisotropy in your model. But here for anisotropic inflation, the anisotropy comes from the background metric, the anisotropy of the background metric, which is the same anisotropy that gives rise to the anisotropic part of the scalar power spectrum. But from observations, there is a very small room for a possible anisotropy of a scalar power spectrum. That is why the anisotropy of the background metric is restricted to a very small number, which in turn is suppressing the scalar tensor, the size of the scalar tensor mixing. And once again, you can check all of these details in these papers. Now, onto the observational implications. Our theory is expected to give rise to a non-zero TB and EB correlations for CMB anisotropy observations. This is because we break the full rotational symmetry. And the correlation here, EB or TB, coming from S and T mixing is non-zero if L and L prime differs by an odd number. If they differ by an even number, this correlation will be killed by parity. So at the end of the day, after some tedious calculations, you can reach the final result of the EB or TB correlation. Of course, here C is a constant term that comes from our model. And the structure A guarantees that L and L prime has to differ by an odd number. And this is something that you can feed into a computer code that will eventually give you the final result that you need to compare with observations. Notice that both tensor-tensor and scalar-tensor anisotropies can source a TB or EB correlations because both of them are anisotropic in our model. But the scalar-tensor one dominates if under the assumption that the size of the mixing is larger than the tensor-scalar ratio, which is also why what we've been assuming up to now. So in our paper, so we only investigate the tensor-scalar mixing contribution to TB and EB. Now, of course, recently there has been a discussion about TB and EB correlations coming from cosmic birefringence. And of course, it will be very interesting to be able to contribute to this discussion by relating our model to data and comparing with the behavior differences of our model and the cosmic birefringence. So in conclusion, we can construct an inflationary model by coupling a triplet of scalar fields to gravity with the triplet satisfying internal icosahedral rotation and translational symmetry. We can further allow for non-minimal coupling, which will give rise to anisotropies in tensor-tensor spectrum and the bispectrum, and also will give rise to a non-vanishing scalar tensor spectrum. But at the same time, we will be preserving the isotropy of scalar spectrum and the background metric. In our model, the scalar tensor amplitude can dominate over the tensor-tensor amplitude, and it can feed non-zero TB and EB correlations for CMB anisotropy observations. And I am working on relating our model to actual observational data. This is the end of my talk. Thank you for your attention.